kids! Hey! We're going to do this problem. It says, during a thunderstorm, winds with a speed of 47.7 meters per second, roughly, over 90 miles an hour, 95-ish miles an hour. It can happen during a thunderstorm. It could be a really bad storm. Blow across a flat roof with an area of 668 meters squared. Find the force, magnitude and direction, remember force is a vector, acting on the roof. And then it tells us density of the air, 1.29 kilograms per meter cubed, which is pretty standard for the density of air right around sea level. All right, so if we're doing this problem, first of all, you have to recognize, I have moving fluid. So if you have moving fluid, you should be thinking about Bernoulli, which means, I need to draw my picture first because I always draw my picture. So let's draw a picture of what's happening. So, all right, so I have my house. Here's my building with a flat roof. Inside the house, the air, surprisingly, is not moving. And then outside, the air is rushing over top at 47.7 meters per second. So then, all right, so then what are my important points? Well, right on top of the roof and right underneath the roof. Those are going to be my important points. So I need to write out my Bernoulli equation. So let's write it out. I'm going to call that A, that B. So rho G Y A plus 1/2 rho V squared at A plus the pressure at A equals rho G Y at B plus 1/2 rho V B squared plus the pressure at B. Now you might be thinking, all right, well, I don't see force anywhere in this equation, but it's there. It's actually going to be related to pressure. So remember, pressure is force over area. So if we can find the difference in pressure, we can find, and we know the area, which we do, we can find the force that's going to be exerted. So let's go through and let's figure out, hey, are there some things that we can cancel? Are there things that are going to be the same and things that are going to be zero? Well, inside here at point B, I know my pressure. Okay, well, what's the pressure inside the house? It's going to be 1 atmosphere, which is, the College Board says, 1 times 10 to the 5th pascals, okay? If you're really doing at the surface of the Earth, typically it's like 101 kilopascals, but whatever, this is according to the College Board. And then you can say, well, the height difference here is going to be really, really small, so we're going to just make that assumption. There is no height difference. Inside, my air is not moving at all, so that's going to be 0. So look, the whole right side, I got simplified down to this. Now on my left side, I'm going to plug my stuff in. So 1.2, my rho is 1.29. My V is 47.7 squared plus my pressure here. So now I'm going to do some math and figure out what my pressure on the inside is. So handy dandy calculator, let's do it. All right, so I'm going to get 0.5 times 1.29 times 47.7 squared. That number is 1467. So I'm going to take 1E5 minus that number, and I get my pressure to be this number, 98532.4 pascals. So that means the pressure inside the building is this. The pressure outside the building is this. So then we need to find the change in pressure. The change in pressure, so 1E5 times or minus that answer, and I get the change in pressure is going to be 1467.6 pascals. And then remember, pressure is force over area. So if I plug it in, 14,667.6 equals force over 668. So multiply by 668. And I get my force, which is really big. 9480331.4 newtons. And then I need to figure out which way it's going to point. So in this case, higher pressure, lower pressure. Remember, fluids always go from high pressure to low pressure, so the force would point up. And yes, there has literally been cases where during really bad tornadoes and storms like that, our roofs have literally been blown up off the house because of the wind blowing across. There you go. Bye, kids.